For page 21 of the scheduling notes, we're going to go to Learn and grab a handout. So go to Lectures, Lecture Handouts, and we're going to download the scheduling template again. And you can either fill out the bottom half of the template this time if you already have it printed, or fill out the top if you want to fill out a second copy. So this is going to be our rate monotonic with fixed priority preemptive scheduling. It's usually just called rate monotonic. And our task set again, task 1 has a period of 10, worst case execution time of 2. Task 2 has a period of 12, worst case execution time of 3. And task 3 has a period of 6, execution time of 1. The processor utilization for this task set is about 62%. So this is going to be the first example we're going to see where there's idle time, or time where the idle task is running, and that should add up to 38% of the time. Now, this is also the first time that we're filling in a schedule for something that's going to be scheduling dynamically. So we'll assign the priorities statically. So let's do that right now. And so it's inversely proportional to the period. So task 3 will have the highest priority. So let's say first, so it's not confusing. Second and third. And so we could fill in this table for any number of time units because our application will run indefinitely, but the least common multiple of these 3 periods is 60. So let's do that. And so I'm going to number or put a time with each block. So each segment here will be 3 timed units. $42, $45, $48, $51, $54, $57, $60. Okay, I can count by 3s, that's good. And the one thing that we need to know for this example, which I haven't given yet, is what is the time slice, because it's going to possibly switch between tasks of equal priority for a time slices unit. Now in this case it really doesn't matter because they're all different priorities, so whoever's the highest priority that's ready to run, that's the one that'll run. But in general, if I had a couple tasks that had the same period, they would have the same priority, and then you would need to know what the time slice is. So we'll assume here time slice equals 1 unit, whatever that is. And maybe I'll show you an example below where that actually matters. So the next thing to do is to fill in the release dates. So all 3 tasks are released at time 0. Task 1 is released every 10 time units after that. I'm not going to number the release dates. I think we should be able to tell and 60. Task 2 is released every 12 time units, so that'll work nicely here. 12, 24, 36, 48, and 60. And likewise, task 3 works nicely, so 6, well, twice as often. 6, 12, 18, 24, 30, 36, 42, 48, 54, and 60. Okay, so they're all released at time 0, and task 3 is the highest priority, so it will run. And its worst case execution time is 1 time unit. So it will finish at time 1, and then the next highest priority task will run, which is task 1, and it has a worst case execution time of 2 time units. So it will finish at time 3, and at time 3, task 2 is the only task left that's ready to run, and it runs for 3 time units. So it's going to fill in the time from time 3 to time 6. Now at time 6, task 3 is released, so it's ready to run, and again it runs for 1 time unit. At that point, neither task 1 nor task 2 are ready to run, so we are going to have an idle period from time 7 to time 10. So the processor will be idle during that time. At time 10, task 1 is released again, and it will run for 2 time units. At time 12, 2 and 3 are released, and since 3 is the higher priority, it will go first, run for 1 time unit, and then task 3 will run for 3 time units from 13 to 16. And next we have another idle period from time 16 to 18. At time 18, task 3 is released again, so it runs for 1 time unit. And we have a small idle period from time 19 to 20, and now task 1 is ready to run for 2 time units, so it'll run from time 20 to 22. And again, we have another idle period from time 22 to 24. At this point, task 3 will run for 1 time unit, followed by task 2 for 3 time units. It's time 25 to 28. And we have another idle period of 2 time units from 28 to 30. At time 30, task 1 and task 3 are released. Task 3 will run first because that's the highest priority, and then task 1 will run for 2 time units from time 31 to 33, and then we have another idle period of 3 time units from 33 to 36. At this point, task 3 runs again for 1 time unit, and then task 2 runs for 3 time units, and then task 1 is going to run for 2 time units, and then task 3 for 1 time unit, and then we have a long idle period of 5 time units. So at time 48, again the high priority task that's ready is task 3, followed by task 2, which has a worst case execution time of 3 time units, but it's going to be preempted by task 1 when task 1 is released at time 50, because it has a higher priority than task 2. So task 1 will run for 2 time units from time 50 to 52, at which point task 2 can finish the remaining 2 time units that it needs to run. And then at time 54, task 1 is released and runs, and then we have idle time for 5 time units. And at time 60, the whole pattern repeats again. Okay, let's continue with another example just to make sure that you're getting the details. So we're going to do another rate monotonic with fixed priority preemptive scheduling. And we'll have 2 tasks with period 50 and 1 task with period 60. And worst case execution times of 15, 10, and 10. So for this, if you calculate the processor utilization, it's approximately 0.67, and so that checks out. And the product of 1 plus the task utilizations is equal to 1.82, which is less than 2, so that's good. So it's schedulable via rate monotonic priorities with fixed priority preemptive scheduling. And in this case, let's just say that our time slice equals 5 time units. And we will use, each segment will be 5 time units. And let's just go up to time 60. That will be enough for demonstration purposes. So they're all released at time 0. And so the priorities, I'll write to the left here, will be tied for task 1 and task 2. So they'll both have first priority, task 3 will have second priority. So task 1 and task 2 are going to alternate time slices. Which one runs first is an arbitrary choice. Let's just say that task 1 runs first. Runs for 5 time units and it gets preempted, and task 2 runs for 5 time units, at which point it's preempted. Task 1 runs again, and it's preempted, and task 2 runs again. At this point, task 2 has finished its 10 time units of execution. Task 1 has not. It will run for 5 more time units. So now it's done. So task 1 and task 2 don't get released again until time 50, and task 3 at time 60. So at time 25, the only task that's ready to run is task 60. It's been waiting, and it will run for 10 time units uninterrupted, at which point we will have an idle period until task 1 and task 2 start again, or are released again, at which point one of those two will run first. So let's just change the order this time. Let's say that task 2 runs first, and then task 1, and so on. And I just want to make one more point before finishing this page. First, let's number it. This was page 21. Okay. So with the first example here, we did the least common multiple of the time periods, of the task periods, which is 60. So we can count the idle time, and if you do that, there are 23 units of idle time, and if you divide that by 60, that gives you roughly 38% idle time. Processor utilization was 62%, so those add up to 100% if you calculate them exactly. Now in the second example at the bottom here, the least common multiple of 50 and 60 is 300, sorry. And so we're not going to fill out that whole thing. If you fill out the timeline for 300 time units, you could count up the idle periods and divide them by the total time by 300, and it should give you 100% minus, it looks like 66.6%, so it should give you 33.3%. But here we haven't done a complete least common multiple, so if we just counted those 15 time units and divide by 60, we're going to get 25%, which is not accurate because it's not the complete, it doesn't show all the permutations.